So we're starting chapter 6 in this video, and we are going to talk about what are known as absolute extrema. And we've seen this word extrema before. Uh, Extrema is just talking about, it's the plural of extreme, and maxima, minima, that kind of thing. So absolute as opposed to relative is over the entire domain that you are looking at of a function. It is either the absolute max or the absolute minimum, as opposed to the relative, where the relative is just looking in a particular neighborhood. That particular value is the maximum in that neighborhood. So just to kind of illustrate these ideas, we have a couple of pictures here where so the absolute maximum again is just the maximum value of the function over the entire domain that you're looking at. So it doesn't have to be the entire domain of the function, but it's the domain of interest, I guess you could say. And then here we have the absolute minimum, just basic linear function here. This one's a little bit more interesting, I guess. So here we have an absolute minimum. This is the lowest point of this function in this domain. Here is the absolute maximum. Here we have a relative maximum because of the derivative would be 0 here, and it goes from increasing to decreasing. So, of course, with the absolute maximum, the derivative will be increasing and then decreasing, but this value of the function is going to be greater than any other value of the function at any other point in the interval that we're looking at. So again, doesn't have to be for the entire domain, but we do need a closed interval, and then we can find an absolute max or min. And that's what the extreme value theorem here is talking about. So a function that is continuous on a closed interval from a to b will have both an absolute maximum and an absolute minimum in the interval. And here we see where the continuous part is important, because here we have a function that has vertical asymptotes at a and b. So it's not continuous over that closed interval. It's continuous over the open interval, a to b. But in this case, we have an absolute minimum, but over the closed interval, we don't have an absolute maximum, because you could always find, no matter how close you get to a or b, you could always find a value that's going to function, a value that's going to be greater than another one. So over the open interval, it's not going to work. And then if there are discontinuities, like in this case, there's no maximum value here because the value of the function at x1 is f of x1, which is here. If you're coming from this direction, you can always get closer to this point. So whatever point you pick, so pick x1 minus some very small number. You call it epsilon. X1 minus epsilon, some very small number. So you're really close to x1. But you can always get closer. So we're talking about the real numbers. You can always get closer to that value, and as you get closer, it's going to increase, but you'll never actually get there. So this one is discontinuous, so the extreme value doesn't apply. This one, more than the discontinuity, I mean, it's continuous over the open interval, but it's not continuous over the closed interval. So that's the important part there. All right, well, so it's a very easy concept to get, and these are actually very easy problems to solve. So finding the absolute extrema over some closed interval. Step one, I've mentioned this a few times in the last several sections. Step one is to take the derivative. So most of the problems that we're seeing now, the first step is to take the derivative, and more importantly, we're going to find the critical numbers in this open interval a to b. Then evaluate f at each critical number. Now this is the part where you might need to think about what we're talking about. We're talking about the absolute extrema, the absolute maximum, or the absolute minimum of the function. Now, when we're finding relative max and relative min, we would find the critical numbers and then say 0 is a critical number and 1 is a critical number, and then we'll test these intervals to see if the first derivative is positive or negative. So we evaluate at f prime if we're looking for the relative max or min. If we're talking about a continuous function on a closed interval, then we really are just looking at the values of the function. So we don't really need to worry about if the derivative is positive or negative. We can just look at the values of the function at each of these points. And then we need to evaluate f of a and f of b. So we're not evaluating anything in the derivative. We're finding the critical, we're using the derivative to find the critical numbers. But then once we get past step 1, we don't need the derivative again. So then the largest value from steps 2 and 3 is the absolute max on this closed interval a to b. And then likewise, the smallest value is the absolute min. So all we're doing, take the derivative, find the critical values, then plug each of those numbers, critical numbers, into f, not the derivative, but the original function f, evaluate it at the endpoints, and then we're just going to compare the numbers. So for instance, here is a function. Let's just say that we'll call this a, we'll call this b over here, and let's say this function goes like this. Well, where is the derivative 0? The derivative will be 0 there and there. And so we'll find f of a, we'll find f of b, and let's call this critical number C1 and this critical number C2. So we'll find f of C1, find f of C2, and then in this case, f of a is the smallest and f of b is the biggest. And there you go. And those would be your max and your min. If you had another one, and I won't do all the details, but if it looked like this over the closed interval, now here's your max and here's your min. And you'll find that by finding the derivative, evaluating at the critical points, and then evaluating at the endpoints. So very easy process, and I think it makes pretty logical sense how this works. So let's we're going to look at 2 examples. So here's an example. And this one, I think this example maybe trips people up with the algebra more than anything else. So we're not used to working with fractional exponents too much. I mean, you do a little bit, but when you're asked to solve this equation, how do you go about doing that? Well, we're going to factor out 8/3. So we can factor out, when you have fractions, typically factor out the smallest one. It doesn't really matter too much what it is, but I mean, these are usually set up to work out pretty nicely. But 8/3 is less than 32/3, so you pull out an 8/3. With the exponents, now this is the way you should always do it with the exponents, pull out the smallest one. So regardless of sign, pull out the smallest exponents. We're going to factor out x to the negative 1/3. Then what are we left with? Well, to figure out so obviously we factored out the 8/3, so we're just going to have x to some exponent. Figure it out. What do we need? Whatever this one is plus that one has to equal that one. So this will be an x squared. So if you take 2 minus 1/3, that gives the 5/3. And you could also think about it, if you multiply these two together, you should get this. And the way you'd multiply these two together is you'd add the exponent. All right, then the next term, we have a 4 left. And then x to the negative 1/3, x to the negative 1/3. So there's nothing left there. And again, if you're not comfortable doing these where you have to factor out a fractional exponent, once you get here, just see if you can distribute back and end up where you were. So you can check your answer pretty easily and make sure that you're right. Now, x equals 0, so this is obviously in the denominator. So x equals 0 is not really in the domain of the derivative, but is still a critical number because it is in the domain of the function. And then this one will be x equals 2 and x equals negative 2. So here are our critical values. Now notice the interval is negative 1 to 8. Negative 2 is not in that interval, so we really don't need to worry about it because it's not even in the interval that we're considering. So we found our critical numbers, 0 and 2. And then now we just need to evaluate f of negative 1, f of 8. So the endpoints of the interval and each critical number. So f of 0, f of 2. Now notice again, evaluating in the original function, not the derivative. So the original function, not the derivative. So let's see what we get. And obviously, you probably need a calculator for some of these. F of negative 1 I have is negative 15. F of 8 I have is 192. F of 0, of course, is 0. And then F of 2 is going to be negative 19.05. So now if we look at all these, what is the smallest number? That would be this one. So this is our minimum, our absolute minimum. And then where's the biggest one? This is the biggest one. So this is an absolute maximum. That's really all there is to it. So it's not nothing super complicated, not a lot of steps here. I think the biggest problem probably will be either finding the critical points because of the algebra or forgetting that you need to plug into the function. Maybe you plug into the derivative instead, accidentally forget that. So remember, plug into the original function. All right, next one, just easy polynomial here. So we take the derivative, negative 4x cubed minus 12x squared plus 16x. And then let's set it equal to 0. Let's factor out a negative 4x from this. We have x squared plus 3x minus 4. And so we get factored that second part, and we get x plus 4, x minus 1. So we get x equals 0, x equals negative 4, x equals 1. Now notice all of these are in the intervals negative 5 to 5. So all of these are critical numbers that we are interested in. So now we just need to get f of negative 5, f of 5, and then f of 0, f of negative 4, f of negative 1. And then we'll compare all these values. So f of negative 5 is 95. F of 5 is negative 905. F of 0 is 20. F of negative 4 is 148. And then F of 1, positive 1. F of 1 is 23. All right, so now the biggest number among these is going to be f of negative 4, and the smallest number is going to be f of 5. So there is our absolute minimum, and here is our absolute maximum. And that's all there is to it. So you just take the derivative, set it equal to 0, find the critical numbers, and then plug those critical numbers and the endpoints of the interval back into the function, and then see which is the smallest and the largest. So fairly straightforward.